Right, let's press on. Okay, so last time I started talking about the various sorting algorithms, and I started with selection sort. And it's a very simple algorithm, simply a number of passes across part of the array. On the first pass, you simply find the smallest element in the array and put it at the front. You then, once you've done that, you know that the smallest element's at the start, so you can forget about that. You start at the second element, scan the rest of the array, find the smallest element in that, put it at the front. How do you put it at the front? Well, you simply find where's the smallest element. You know that you're dealing with the second position, and you can simply swap those two elements. And if you just keep doing that, you get more of the start of the array is always sorted. The rest of the array you don't know, but you simply keep looking for the smallest element that's left and move it into its appropriate position, and by the time you've seen the whole array, you've sorted everything. So if you wanted to describe that algorithmically, you can do something like this. So I tells us where we're starting from, and so we're going to try and find the smallest element in the rest of the array after I, and including I. And once we found the position of that smallest element, we swap it with whatever's in AI. So how do we find the index of the minimum value? Hopefully that's really straightforward. We simply assume that the first one's going to be the smallest and then scan the rest, looking for anything that's smaller. And if we find something that's smaller, we just remember where did we find it. So last time I said that the first time we scan through most of the array, we do n-1 comparisons. Having done that, we've got the smallest element at the start, and we consider less of the array. So then we do n-2 comparisons, then we do n-3, then n-4, n-5, and so on until we've sorted everything and we're down to the last one. So the number of comparisons that we do is just the sum n-1, n-2, down to 1. Bit of rearrangement, you can get that as n squared minus n over 2. And remember that I said when we're dealing with complexity, we don't care about lower ordered terms and we don't care about constants. We're just looking for the highest ordered term, because that's the term that's effectively going to determine the shape of the graph, whether it goes linearly, whether it's a bit flatter than that, or whether it goes up like that. So this one comes out as n squared over 2 minus n. We forget about minus n over 2. We forget about n over 2. That's a lower order term. We got n squared over 2. We forget about dividing by 2. And we come up with order n squared. The number of swaps we do exactly one swap at the end of each pass through the array. So we do n-1 passes, therefore n-1 swaps. And the other thing about this algorithm is it's not at all adaptive. It always takes the same amount of time, regardless of how sorted the original array was. And if we want to have a look at an implementation, so here are the functions that calculate the various properties of interest. So we got a function less that simply does a less than comparison, but also counts the number of compares. Equality, I don't think I actually used that anywhere. Swap, we'll do a swap and also count the fact that we've done an extra swap. And moving two things, copying an element from one place in the array to the other, counts as a move. And if you want to copy an entire array, there's a function to do that, and that involves a whole lot of moves as well. All right, let's jump down to it would have selection, so it would have to be right at the bottom. All right, so here's the C version of that algorithmic description that we just looked at. Iterate from low up to high. Remember, all of these algorithms, they're not necessarily sorting an entire array. They're sorting a subsegment of the array, starting from position low, index low, up to index high. And if it so happens that index low is 0 and index high is n-1, then we sort the whole array. Alright, but in any case we iterate from low up to high. The first thing we do is find out what value belongs at position low, and then we go position low plus 1, what value belongs there, position low plus 2, and so on. Here you can see we're making a call to less, so that's going to count a comparison each time, and here we're making a call to swap. And in the middle, this for loop here is basically finding the index of the smallest element in the current interesting section of the array. And that's what I wanted to do. And to demonstrate that it's not, let's see, I'll just pick a moderate size array. If the array is in ascending order, it takes that long. If the array is in random order, it takes that long. If the array is in descending order, it takes that long. Always the same. Okay, so it doesn't adapt to the sortedness of the original array. Alright. Next, bubble sort. Basically what bubble sort does, it makes passes along the array, and you can go in either direction. I can't remember which direction we go. I think what we do is we move small elements. So it starts at one end of the array, looks for adjacent pairs of elements that are out of order, swaps them over, and keeps moving down the array. And if you think about what's going to happen when you do that, once you find the smallest element, it's always going to be smaller than the adjacent element when you do a comparison, so it's going to be swapped and swapped and swapped and swapped and swapped, and eventually the smallest element's going to work its way to the front of the array in a single pass. Having done that, you've kind of achieved the same effect that you achieved with selection sort. You've put the smallest element at the start. You can then go from the end of the array down to the second element and do the same process. Any adjacent elements out of order, swap them over. And the second smallest element is going to drift its way to the front of the array. So, I mean, that's how it gets the name. The kind of the smallest element drifts to the start, the second smallest element drifts to the second position, the third smallest element drifts to the third position. So you get some behaviour kind of like that. So the first pass through the array starts at 2, that's smaller than 5, so we'll swap them over. We'll then compare 1 and 2, well 1 is smaller, so we don't swap. 6 and 1, 1 is smaller than 6, we swap. 1 and 4, 1 is smaller than 4, so we'll swap. 3 and 1, 1 is smaller than 3, so we'll swap. So 1 ends up at the start of the array, okay, after that first pass. In the second pass, we start at the top again. Well, 2 is less than 5, so it stays where it is, but it's smaller than 6, so we do a swap. Smaller than 4, we do a swap. Smaller than 3, we do a swap, and we end up with that. We'll then do another pass through the array. 5 is smaller than 6, so we do a swap. I think we keep going. We compare 5 to 4, we don't do a swap. We compare 3 to 4, we don't do a swap. And that's where we'd stop here, because we know that the first two elements are the two smallest elements. We then do another pass through the array, and we'd say, well, no swap needed there, no swap needed there, no swap needed there, so the array must be sorted already. So then we can stop. You can write bubble sort so that you don't do that check for the number of swaps, in which case it behaves even worse than selection sort. So this is the algorithmic description. We simply scan along, swapping out of order elements, the diagrammatic description rather. So after the first pass through the array, the smallest element's at the front. Do it again, second smallest element is second. Do it a few more times. This whole part of the array is sorted, and the very last time you're just comparing the last two elements, and if they're out of order you swap, and the whole array is sorted. If you want to describe that algorithmically, you can do it like this. So notice that this inner for loop runs backwards from the top of the array down towards I. And we're comparing adjacent pairs of elements. So if the value in the current element, if you like, is smaller than the value in the preceding element in the array, then we swap them over. And you can see one thing that we're doing, we're counting the number of swaps. At the start of each iteration, we assume that no swaps are going to happen. If a swap does happen, then we count it here. And if we manage to make an entire pass through through part of the array that isn't yet sorted, but we don't make any swaps, then the part of the array that isn't yet sorted is actually sorted, so we can stop. What about the cost analysis? Well, this one's a little bit different to the previous one. The previous algorithm always cost exactly the same. In this case, it depends. So bubble sort's an adaptive algorithm, certainly the way it was written there. So for the ith iteration, we know that we're going to do n minus I comparisons for sure. Right? So the first iteration, we scan all the way back to the first element. Second iteration, we scan all the way back to the second element. So the number of comparisons is going to be one of those n squared functions. So n minus 1 plus n minus 2 plus n minus 3, How many swaps do we do? Well, that varies depending on the orderedness. If the array starts out in order, then we don't do any swaps. So in the best case, we don't do any swaps. In the worst case, we do n minus I swaps on each iteration through the array, each scan of the array. How many scans of the array do we do? Well, it depends on the orderedness, because we've got that condition that if we don't do any swaps, we stop scanning through the array. So if that gets triggered at any point, then we're not going to scan n times. So in the worst case, we are going to have n iterations, n scans through the array. Each scan through the array results in n minus 1, n minus 2, n minus 3 comparisons and some number of swaps. In the worst case, it'll be n minus 1 swaps. Can anyone suggest when that worst case is going to occur? I haven't got, oh damn, I have got it there. Right. So when the array is in reverse sorted order, we always swap. So if you think about that, if we've got 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 1 is at the end. On the first pass, 1 is going to be bubbled down to the start. On the second pass, 2 is going to be bubbled down to the second position. Third pass, 3 is going to be bubbled down to the third position. So that's the worst case scenario is an n squared term. So overall, we quote the complexity of bubble sort as n squared. So both of those algorithms are n squared, but if you look at the actual formula, it's a little bit different. And certainly, bubble sort as a best case scenario, if the array is already sorted, we're going to scan backwards through the array. We won't do any swaps because we'll never find a pair of elements out of order, and we'll reach the start of the array. N swaps will be equal to 0, and we'll break straight away. So we'll do a single pass through the array, and that'll be it. And we can see that if we do bubble sort, let's start with random. So that's the number of comparisons and the number of swaps. If the array is sorted in descending order, that's the worst case scenario, so that will have, better have more, or it has a couple more comparisons, but certainly it has a lot more swaps. Okay? And if the array is in ascending order, we see quite different behaviour. We should see maybe 4,999 comparisons, no swaps, and that'll be it. So something like that, right? So if the array is already sorted, bubble sort's a good way to sort it. But I guess you could always just do any sorted check and then stop there if you really wanted to. But in general, it's order n squared, so it's not a great algorithm. to use. And when if you're talking about order n squared, I say they're not good algorithms, but if you've got 100 elements to sort, it's probably all right. You can use something like that anyway. All right, insertion sort. A slightly different behaviour, and this is one of the algorithms that does, rather than swaps, it does moves. So you take the first element and you say, all right, that's a sorted array of length 1, and any array of length 1 is sorted. So then you go to the second element, and the idea here is that you want to push it into its correct position in the sorted part of the array. And you do that by moving any elements that are larger than the current element up. So you move them up in the array. And you keep doing that, you'll eventually push the current element into its correct position. Let's have a look at the... I have a feeling the diagram is a little bit crappy. Yes, it was. So we've got this part of the array that's sorted, okay? And we take this element here and we scan backwards through the sorted part of the array, looking for an element that's smaller than the current element. As soon as we find that, we know that the current element that we're dealing with belongs in the next position up from from the element that we found. As we scan, we move each of the elements in the sorted part of the array that's larger than the current element up to the next position. So we just push everything up as we scan down. And by the time we reach the correct position, we've moved something out of the way so we can just drop the current element into that position, increasing the length of the sorted part of the array by 1. And so the first thing we do, a useful way to start this off is to find the minimum value in the array and put it in the first position. So then we know for sure that that first position is a sorted part of the array and it's not going to change. So then what we do is we go to the next position and we move backwards and decide, do we have to push anything out of the way to make way for the current element? So one thing that we have to do, because we're going to move things along, the very first time we move something along, we overwrite the current element. So we grab a copy of that. So in some ways, this, if you know how a swap works, where you're swapping the values of two variables, you've got to save a copy of one of the variables, then copy over the top of it, and then take your saved copy and put it into the other variable. You're doing a similar kind of thing here. So we're saving a copy of the current element, calling it V, and then we're scanning backwards from that position, looking for an element that's smaller than V. So while V is larger than the next element down the list, we keep going. And sorry, if V is larger than the next element down the list, that's the point where we stop. If the element that we're looking at is larger than V, then we move that element up by 1 position and we just keep pushing things up by 1 as we move down. And eventually we find the right spot to put V, and so we stick it there using that statement. So the cost for doing that, once again, this is an adaptive algorithm. How many comparisons we do depends on how sorted the algorithm is. In this case, we never do a swap. What we're doing is we're actually doing moves in the array. And how many moves do we have to do? Well, that depends where this element fits. So we take this current element, this part of the array is sorted, we start looking for where it fits. If it fits near the top, we're not going to do many moves at all. If it fits somewhere near the bottom, because it's a very small element, then we're going to do a lot of moves. So that it all depends. And in the best case, we do 1 move. In the worst case, we do a whole lot of moves. We always do n iterations. In the best case, and like for bubble sort, the best case cost for this algorithm is if the array is already sorted. So you'll put the smallest element at the start, well, it was already there, so that's nice. You'll look at the second element, push it down to where it belongs, well, it belongs where it currently is, so we don't have to move anything, and that process is going to appear the same for all the other elements that we look at. We'll discover straight away that they don't need to be moved. And like bubble sort, the worst case happens to be when it's reverse sorted, because you're always going to push this small element, or you're going to push everything up to make room for the small element at the start. So the complexity is n squared once again. So we can check out those claims. Let's pick the worst case scenario, insertion sort on a list of 5,000. Sorry, that's the best case, duh. Why is there one swap? Why is there one swap? Interesting question. Why is there a swap? Let me... That's more one of them. Why have I got a swap? I know why I've got a swap. Ha! Why have I got a swap? Because in the algorithm it said find the smallest element and put it at the start. So we scan through the array once, find the smallest element, and then we swap it into the first position. Okay, so we always do that. But then the rest of the time we're simply moving things around. So you can see when the array is in ascending order, we don't have to move anything. If the array is in random order, we do a lot of moves, we do a lot of comparisons. If the array is in descending order, I think the situation gets even worse, and you can see those numbers are quite a bit larger. Just to indicate that it's adaptive, if we keep generating random numbers, the amount of sortedness is going to change each time, and so we wouldn't expect the number of comparisons to be the same. So depending on how sorted this random array is, we're going to end up with different number of comparisons. So it's adaptive but not adaptive in a, well, it is adaptive in a good sense. If the array is already sorted, then we don't have to do too much work. Alright, so that's insertion sort. Next algorithm, quicksort. So the basic idea with quicksort is that you want to make progress towards the array being sorted by putting all the small elements at one end and all the big elements at the other end. And if you can at least achieve that much, you've done some sorting. If you then take the first part of the array and you sort that recursively using quicksort, then you can then you've sorted all the small elements. You got all the large elements up here. If you sort them using quicksort, then you've got the whole array sorted. Okay, so that's the strategy. So it's a recursive description of the algorithm, and it basically works like this. We have two phases. We have a partitioning phase where we do what I just said. We want to have all the small elements at the start of the array, not necessarily sorted, and all of the large elements at the other end of the array also not necessarily sorted. And when you say small and large relative to what? Relative to an element that we choose, and which we're going to call the pivot. So by the time you finish this first phase, the partitioning phase, small elements to the front, large elements to the end, we've got the pivot in its correct position. So in some sense, we've sorted one element of the array somewhere in the middle. All of these elements are going to be less than the pivot. All of these elements are going to be greater than the pivot. If we then sort this part of the array, then we've got all the elements less than x and they're sorted. Then we've got x, and if we sort this part of the array, then we've got all the elements greater than x and they're sorted. Therefore the entire array is sorted, which is indicated by that green underlining. So the expression of the algorithm is actually very nice. So to quick sort an array from low to high, well, first thing, since it's a recursive description, we need a base case. When do we know to terminate the algorithm? Well, we can terminate the algorithm if we've got only one element in the array, or because we've got these low and high bounds that are actually moving towards each other, it's possible that they cross over. So we have, as soon as the high bound is either equal to the low bound, which means we're dealing with a single element array, which must be sorted by definition, or if high actually happens to overshoot low, then we know that there's nothing to look at. So the first step is to do this partitioning, where we grab a pivot element, choose an element to be the pivot, and then make sure that everything in the first half of the array is less than the pivot, everything in the second half of the array is greater than the pivot, and then we recursively sort those two subparts of the array, and that's going to give us overall a sorted array. So how does the partitioning phase work? Well, basically what we do, for the time being, I'll just choose the first element as the pivot, okay? And then what we do is we have two indexes. One starts at the next element beyond the pivot, one starts at the top end of the array, and they move towards each other. And as they're moving, if we see an element that's less than x, then we just ignore it, because we know it's in the correct position. It's in the lower part of the array, and all the elements in the lower part of the array are supposed to be less than x. Eventually we might bump into an element that's larger than x. If we do, we'll stop. And we'll also do the same thing with j. J will come down from the top end of the array. If it sees an element's larger than x, it just keeps going. If it eventually finds an element that's smaller than x, it stops. And then what we do is we've got a large element in the small part of the array, and we've got a small element in the large part of the array, so we swap them over. So we do that, and then we continue. And we just continue until I and j meet somewhere in the middle. And in fact, the point where they meet is the point where we're going to put the pivot into the array. So eventually I and j meet, and they meet, and it depends how you structure the while loops, but let's say for the sake of argument they're going to meet at a point where we've got a small value. So we've got the pivot at the start, we've got a value smaller than the pivot at the point where the pivot wants to go. So the obvious thing to do is simply swap those two things over. X moves into its correct position in the array, because everything is less than x down here, and everything up there is greater than x. And so the array, you might say that's stupid, because all you've managed to achieve is getting one element in the correct position. But what you have managed to achieve, that you've at least put the small elements at one end and the big elements at the other end. Now that's all very nice, assuming that x is a sort of middle element. If x is not a middle element, things can go horribly wrong. Well, not horribly wrong, but not nice. So let's say, for the sake of argument, that x was the smallest element in the array. I will go nowhere because everything's going to be larger than x, so I will just stop. J will come down, 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 and eventually meet I, and not find any elements that are smaller than x. And so the pivot is going to end up at the start of the array. Right, so all we managed to do, in the same way that bubble sort and selection sort work, we managed to put the smallest element at the start of the array. So the partition step here, we've got x at the start and everything else at the end, and then we do a quick sort. So going back to that other diagram, so it's kind of like we always end up with the pivot at the start of part of the array, and there are no elements in the array ever less than the pivot. And remember that we're doing recursive calls to quicksort, so we'd be initially quicksorting the entire array, so we end up with a single partition that's everything else apart from the pivot, which is the smallest value. We'll then have a recursive quicksort on that part of the array, and we'll end up with that pivot there, and then we'll then do a recursive quicksort on that part of the array, have a pivot there, and so on and so on. So we end up doing n minus 1, n minus 2, n minus blah, blah, blah. So in the worst case, where the array is already in sorted order, quicksort behaves like n squared. So you might say, why is that quick? It seems no quicker than bubble sort or selection sort or insertion sort. Well, the trick is, if we actually happen to get a pivot that comes somewhere near the middle of the array, then we've made some progress. And what we're interested in is we're going to make, essentially the way I and j come together in the partition, we're going to make a complete pass through the whole array each time. Even when we've got partitions that we're recursively sorting, we're going to look at all of these values, and we're going to look at all of those values. So pretty much we're looking at the whole array at each level of the recursion. And so then the question becomes, how many levels of recursion are there? If we keep splitting the array in half each time, and the pivot always comes in the middle, then how many times can you split the array in half before you come down to single elements? Log 2, like we had with some other example before. So the number of recursive levels, if you like, is going to be log 2. If we look at each level, we're pretty much looking at the entire array. So the total cost that's going to accrue is log 2 levels. On each level we do n comparison, so we end up with an n log n term. So in the average case, quicksort is n log n, which is much better than bubble sort, selection sort, insertion sort, which are n squared in the average case. So that was pretty much what I just said. And as I also pointed out, if we unfortunately choose the smallest element each time as the pivot, then we end up with an n squared algorithm, which is just as bad as all the others. So there for comparison is insertion sort. So let's check let's check quicksort on a random array of size 1,000. So we're talking a lot of comparisons versus a lot less comparisons. And it's a bit funny comparing it against insertion sort because that's all moves. So let's choose one that does swaps. Let's try bubble sort. And there's a hell of a lot of comparisons and swaps going on compared to what you see with quicksort. Okay, so that's why quicksort has the name. Of course, as I said, the worst case is if the list is in ascending order or in fact in descending order. Both of them are bad, and we end up having similar number of comparisons to bubble sort. So it can degenerate depending on the sortedness of the array. Now people have come up with strategies for dealing with that scenario, and one pretty well known strategy is a thing called the median of 3. So rather than always just choosing the first element as the pivot, what you do is you take the first element, the last element and the middle element, and you just choose the middle one of them. And if you're lucky, that middle element will be somewhere close to the middle, so you probably split the array into roughly 2 equal halves. So that's a well-known strategy, and you do that, so you choose first element, last element, middle element, find the median one and move that to the front, and that becomes the pivot, and then you do the standard strategy that we were looking at. Another possibility that has occasionally been used is to assume that the worst case is about to happen. Well, one thing you could do, you could check whether the array is already sorted and then don't bother trying to sort it with quicksort. That'd be another strategy. Another strategy, assume that the worst case is about to happen, that the array is already sorted, and then unsort it. So shuffle it all up, and then call quicksort, and you're dealing with effectively a random sorted array, and you'll get the best case quicksort behaviour from that. In any case, I hope you can see from something like this that there's a significant difference between a fast sorting algorithm and a not so fast sorting algorithm. And there's probably not much going on. I'll do merge sort and shell sort on Wednesday. Okay, that's it.